You may have heard of the three-body problem. The three-body problem. It's not just a book, it's a physics problem. The three-body problem says that there are three masses interacting gravitationally, and there's no generic solution for this motion. You can't just analytical. You can't get an equation of motion for these three objects because this object is pulling on both of these, which makes them move, which changes their position, which pulls on this one. So they all pull on each other, and it's just a problem that there's no default solution. Now, if there's only two objects, yes, we can do the two-body problem. And if there's three objects and one of them is very massive, then you can approximate it like that too. But for the three-body problem, you can just solve it numerically, which is pretty fun and not too hard, and I will do that. But this is a special situation of the three-body problem. So imagine that I have three equal mass objects uniformly distributed in a circle. Can we get a stable motion in this case? Yes, we can. So we're going to find the velocity needed to make these all move. They have to do the same thing. They're all equally distributed. So let's get to two big ideas. Number one idea is that if this is moving in a circular orbit, then the net force on this has to be equal to the magnitude of the net force has to be equal to the magnitude of the derivative of the momentum, or you may just want to say its mass and velocity squared over r. This is true if it's moving in a circular orbit. The net magnitude of that force has to be equal to this expression in order to make it move in a circle. Now, what is the net force on this item, this mass right here? Well, it's the sum of the gravitational forces due to these two things right here. And we can calculate the gravitational force as the gravitational constant g times the product of the masses m1 times m, they're the same mass, divided by this distance squared, and then we have to find it in a vector direction that way. So it's a little difficult in this case to do that, but we're going to do it anyway. Okay, so let's just get started. Let me redraw that picture because I think I'm ready to... What I want to do, let me tell you where we're going to go. Okay, so I'm going to get a new color pencil. Here's purple. Let's just conceptually think about what's happening here and why it might work. Because if I have this distance, then I'm going to have a if I'm thinking about the forces on this one right here, I'm going to have a gravitational force that way. Let's call this 1, 2, 3. So this is F 2 on 1. It's the force that 2 exerts on 1, and it's pulling that way. And there's also a force this way. F3 on 1. If this is equally distributed, then this angle right here and this angle right here, so these two angles and that angle, they're all the same. They're 2 pi over 3. But that means that the direction of this force in the downward negative y direction and the direction of this in the positive direction have to be the same, and the magnitudes have to be the same. So if I add these two forces up, I'm going to get just one force in that direction. So if I just find the x component of this force and multiply it by 2, because that's going to have the same x component, that will be the net gravitational force right here, and I can set that to mv squared over r and solve for that. And then the other two masses are the same, right? Everything is the same. So really, I just need to find the x component of this force, which is easier said than done, but not impossible. Multiply by 2 and set that equal to this and solve for the velocity. That's where we're going to go. Let's do it. And then I'm going to model it in Python because that's what I do. Okay, so let's just draw our circle. And I'm going to say this is my x-axis. This is my m1, m2, but they have the same mass. This is a radius r, and I'm not going to worry about that other mass down here. And I'm going to draw this and this. I'm going to call r. That's I'm just going to use the magnitude. That's the magnitude of the distance between these two, and I need that for the magnitude of the gravitational force. It's going to be g m squared, they both have the same mass, over r squared. That's just the magnitude. Okay. So I need to find that first, and the first thing I need to do is to find r. So I know, let's look at this. This angle right here is theta, and theta is 2 pi over 3. So let's draw, oh good, I got my marker right here, let's use that. I know I can find that and that. This is a value r, so this is the angle, well, I can just do this. I'm going to say this side is going to be equal to, I'm going to call that r2x. I don't need to use purple. That length of the side right there is going to be equal to, the magnitude is r cosine theta, and that's theta. Okay, so if you put in cosine of pi over 2, this is a, cosine of pi over 2 is equal to 2 pi over 3. This is going to be equal to, it's actually a negative r times, what is it, 1/2. Right? You can check that. Let's just, look, I'll prove it to you. Calculator. Degrees, let's change to, how do you change degrees mode? Well, let's see. So cosine, this is going to be 120 degrees. 120 degrees. So that's 60 degrees, right? So this is 60 degrees right there. So I can still use cosine. Cosine is 60. Cosine 60 equals 0.5. So that's that. So that's, this distance is going to be r over 2. This distance right here is going to be equal to r2y is r times the sine of 60, which is the square root of 3 over 2. And you don't, I mean, you could use those as numbers. I'm not going to, because I want to do it as easily as possible. But that's important. So this is r square root of 3 over 2, and this is r over 2. Now I have a bigger triangle right there. So this bigger triangle looks like this. This is the angle r. This is the, I mean, the length r. That's some angle alpha. It's some another angle. I don't really care about it. And this is going to be square root of 3 over 2r, and this is going to be equal to r plus r over 2. R plus r over 2. So it's going to be equal to 3r over 2. So now I have a right triangle. Now I can find r. So r is going to be equal to the square root of this side squared. So it's going to be r squared times 3 over 4, right? That's that squared. Plus this squared, which is going to be r squared times 9 over 4. Now I can factor out the r, so I get r times the square root of, and this get a common denominator of 12 over 4, and so that's going to be equal to that's going to be equal to, I'm having so 12 over 4 is, so r times square root of 3, right? Okay, so that's what that length is right there. Yay! So now I can calculate the gravitational force. F, the magnitude, is going to be g m squared over this squared, which is going to be 3r squared. That's pretty good. Okay, but now I need to find the x component of that force. So we're going to use this triangle again. Let me draw that triangle right here, because that's important for this angle. So this is alpha. This is r, which is the square root of 3 times r. That's right, right? Yep. And this is going to be the square root of 3 over 2r, and this is going to be 3r over 2. So if I draw my gravitational force on mass 1, it looks like it's in the same direction, F. That's a whole vector. But I only want the x component, and that's the angle alpha. So Fx is going to be F times the cosine of alpha. Now, what's alpha? You could find that angle, but I don't care, because I'm going to say cosine of alpha is going to be adjacent over hypotenuse. Well, here's my adjacent. So it's going to be 3r over 2 divided by that, square root of 3r. So r's cancel. and I get the square root of 3 over 2, because I have 3, square root of 3 times square root of 3 divided by square root of 3, one of those cancels, and that's that. That's the cosine of alpha. So fx is going to be equal to g m squared over 3r squared. That was my gravitational force times this, the square root of 3 over 2. And so again, we can do this little cancel thing. I get g m squared over 2 square root of 3r squared. And that's my gravitational force due to one of them. Now F net, magnitude, is going to be twice that. Because remember, I have another force down here due to the other particle. It's going to have the exact same x component. So I'm going to get two of these, and that's going to be g m squared over the square root of 3 times r squared. And I'm going to set that equal to mv squared over r. And I want to find the velocity in order to make these things move in a circle. So this mass cancels, this r cancels, and I get v equals the square root of gm over the square root of 3 times r. Now let's just take it one step further, right? If I do have this velocity, then how long would it take for one thing to orbit? So here's my mass, here's my one mass. I know the velocity, that's a v. I know my radius is r. And so I can say that period t is the total, the velocity is the total distance, 2 pi r, divided by the period. So the period is going to be equal to 2 pi r over v. Oh, one thing I should do is check this, the units. I didn't check the units for this because I know it's right. I'll show you a unit check too. Yeah, I'll make sure that v is correct. So this is going to be, all I have to do is put that in for v, and I get the square root of 3r, times 2 pi r over gm. And that's my period. So how do I know this is the right one? Well, if I just had a single mass orbiting another object, a massive object, then the gravitational force would be g m1, m2, this is m2 now, and this is m1, over r squared. That's the gravitational force, and that's going to be equal to m2 v squared over r. If I solve that for v squared, I get a g m over r square rooted, which is the same things right there. So I know the units work. So that's for a circular orbit. Okay, so we want to test this, right? We want to test and see if this is indeed correct. Let's do a three-body problem the other way. So here's my other three-body problem. And I've already put this in the program, so because I didn't want to waste a bunch of time. So let's draw our three bodies. One, two, three. What I'm going to do is give them all an initial momentum. I'll call that P1, P2, P3. They're all moving in a circular orbit. And I can calculate the gravitational force. So what I want to do is to calculate this vector. I'm going to call this R12. This is the vector from position 1 to 2. And this is going to be R2, 3. And this is going to be R3, 1. And those are all the positions I need. Once I do that, I can calculate the individual gravitational forces. F1 on 2 is going to be negative g mass 1 times mass 2 over the magnitude of R12 squared times R12 hat. So this is a unit vector in the direction of R1. And so this says the gravitational force due to this one is going to be negative because it's pointing that way. The product of the masses, that's easy to do. I need to calculate that vector, R12, and multiply it by a unit vector. Now, how do I find R12? Well, R12 is just going to be the position of R2 minus the position of R1. And now I can do that for all the other ones too. And remember, if I calculate the gravitational force F12, F21, the gravitational force on 1 due to 2 is negative F12 because they're the same force. So if I go back over here, I'm going to say F net 1 is equal to F1 negative F12, because I'm going to calculate that vector. And this is going to give me plus F31. I'll do the same thing for R31. And then that's going to be equal to delta P1 over delta T. That's the change in momentum with respect to time. So if I assume these forces are constant over a short time interval, I can say the final momentum at the end of the time interval for 1, P11, P12, that's the momentum at the end of the time interval. I know the notation stinks. Is P11 plus F net 1 delta T. So I can update the momentum. I can do that for the other objects too. And then I can update the position using the average velocity. R2 equals 2, actually R12 is R11 plus P12 over M delta T. And this is the basic model for the numerical calculations. Do this for all three masses and then do that for every single time interval. I've already done that. I've already written up this program. I haven't put in initial velocities. Okay, I'm not going to go into the details. Let me show you the code, and then we'll put in our calculated velocity and see if it works. So I'm using Web VPython instead of Trinket. It's the same thing. I'm having technical issues. It's it's actually not my problem, but it is a problem. Don't worry about it. I will still give you the code one way or another. So here, and just to make things simpler, I put all the constants as 1. R is 1, G is 1, M is 1. You can do mass of the Earth for 3 Earths. It doesn't really matter. It doesn't matter. Okay. And then I made planet 1, I'm calling P1. Again, it's a poor choice of words on my part, and I apologize. So it doesn't really match up. But P1 for planet 1. It's planet 1. It's a three-dimensional object. It's a sphere. It's on the x-axis of position R00. That's fine. Has a radius, doesn't matter. Has a color, doesn't matter. Make trail, that's useful. Now this theta is the angle between, so I can find the next one, right? So P2 is the next planet, and it's going to be R cosine theta sine theta. That's going to give me my x and y coordinates. The z coordinate 0, and it has a different color. And then P3 is going to be 2 theta away. That's it. So I made the 3 planets. Okay, then I put the initial velocity 0. We can change that. This right here is not what? It's W hat. It's actually omega hat. It's the angular velocity direction. So if that's going to be in the z direction, I need that to calculate the directions of the momentums so that it's perpendicular to the position. Yeah, that's just a little trick. So then I set the initial momentums. They're all 0 in this case because my velocity is 0, but I wanted to make it work right. And then here's my time step of 0.001 seconds. And then I'm going to run it for 3 seconds. Okay. So this first thing, I calculate the 3 R's, R12, 23, 31, just like I said. And you'll notice here that the position of mass 2 is P2.pos. I don't need to say R2 because it's an actual object. So that object's vector location is P2.pos. Is that good? I am going through this fast because I'm just excited. I want to get to the fun part. F12 is the gravitational force on 2 due to 1. So I have G, mass. Norm is the unit vector. So that's R12 hat. That's what that is right there. And then mag takes the magnitude of vector. And then I square it. And then I do the same thing for 2 to 3, 3 to 1. Now here is my momentum update. This is for object 1. You'll notice I have 2 forces, F31, because that's the force due to 3 on 1. F12 is the force on 1 due to 2. So I need a negative sign there because I want the force on 1. So it's negative. And then I do the same thing for 2, same thing for 3, Here I'm updating the positions, and then update the time. So this is three masses that start, and they have zero velocity, so they should just attract. Let's run this sucker. And they blew up, because what happens when they get super close, they're getting on top of each other, the force gets super, super large, and we assume a constant time interval, which is a constant force, which is no longer true, so you get this error. It's not a big deal. Let's go ahead and calculate our initial velocity. So I'm using my equation, just switching back right here. The same one that we had. See it? So I'm going to say v0, the initial velocity, is the square root of g times m divided by the square root of 3 times r. Close parentheses, close parentheses. That should work. Will it work? You never know. Always make mistakes, but let's just see. Very nice. I like that. Okay, I did say I would calculate the period. Let's calculate that. So let's just say, oh, what the heck? T equals, it would be 2 times pi times r over v0. And let's print t equals t. And then in seconds, because, you know. Now, how am I going to get that? I could run it forever. Let's just make a quick graph. I'm going to make a quick and dirty graph. F1 equals G curve. Color equals color.blue. That's not super quick, but that's fine. And I'm going to make that the x position of mass 1 as a function of time. So down here, I'm going to say plot that. So F1.plot time, and it's going to be P1.pos.x. Now, I'm going to have to run this for a longer time. Let's say 6. I'm not sure if that'll make it all the way around. Let's just see. Okay, so there's that. There's my plot. It says 8.2 seconds. So let's see, that's not going to make it. So let's run it for 9 seconds. Okay, so there's that. And there's my no label graph. I'm looking for it to get back up to 1, r equals 1, and how long that takes. And there it is right there. 8.27. 8.27. Winning. Now let me just show you this is a real three-body program, because up here I calculate V0. Let's just make them go half as fast as they're supposed to go. So 0.5 times. And let's just see what happens. Because they all have the same, see, so it's kind of artistic. So still, you know, if they're equal masses, everything's equal, they do equal stuff. And that's kind of cool. Let's make them go a little bit too fast. Let's change this to 1.5, just for fun, because we can. So now they're going too fast. Are they going to escape? Huh. Let's just try a little bit fast. Let's try 1.1. 1.2. Okay, that's kind of cool too. It's very, very mesmerizing. I like that pattern. There's something about that pattern I like. But let's put it back the way it was. 1.0 times that and run it. And like I said, I'm going to give you this code. And if you want to try something for yourself, what if you have 4 equal masses? What if you have, could you do it with 5? Could you do it with any number of equal mass objects equally dispersed? I think you could. As long as, I'm trying to think about 5. As long as the net force on each object's pointing towards the center, then it will work. And you can calculate the velocity. And there you go. The 3-body problem. That was fun. I had fun. Hope you had fun too. Like I said, I'll put the link to the code down below.